All right, this is the AP Calculus AB 2.5 intro video, and we're going to be looking at implicit differentiation and doing one example. All right, so up to this point, we've been differentiating just kind of like typical functions that are solved for y. The truth is that there are many functions that cannot be written explicitly, or it's inconvenient to do that, and so we're going to call these functions implicit functions. These would be functions where, like I said before, the y is not solved for, or it's impossible to solve for it. And so in order to find a derivative associated with an implicit function, we have to use what's called implicit differentiation. So let's review what some of this notation means. So dy dx means this. It means d dx of y, d dx of some function y. And if we wanted to use some words to describe this, I would say this is the derivative of y with respect to x. Derivative of y with respect to x. We've done a few derivatives with respect to t, but most of the time it's been derivative of y with respect to x. The truth is we could do the derivative of y with respect to anything we want, depending on what the situation is. So let's go a little bit deeper here. Let's do a little more specific example. D dx of x cubed, right here. My point for putting this in here is I want you guys to understand that I know we just learned the chain rule in the previous section. The truth is we technically have been doing the chain rule this whole time. So what I'm going to do is I'm going to write this as d dx of parentheses x cubed. And of course, I haven't changed the meaning of this at all. I've just rewritten it slightly so that it looks a little bit more like a composite function like we worked with when we did the chain rule. So I want you to think about this for a second. If this were, we're going to treat this like a chain rule, what would you think of as the inside function? Of course, it would be x, and the outside function would be cubed. So when you think about these boxes getting unpacked, here's how this would look. We would write the derivative of x inside the box cubed would be 3, comes down in front, with the inside box still in there, so 3 parentheses x squared. And then wouldn't we multiply by the derivative of the inside? That's the chain rule, right? So we'd multiply by d dx of x. So what's d dx of x? Well, we could write that a slightly different way. We could just write it as 3x squared times dx over dx. I think you're getting the idea here that d dx of x, no matter how you write it, is just going to be a 1. So this would be 3 times x squared. It might seem like I'm way overcomplicating the issue here because we've been doing problems like that for quite a while, and you probably have very little difficulty with it. But where we're going with next, what I just showed you is going to be quite important. So let's take a look here at another example. This time it's d dx of y cubed. Now I want you to see the consistency here. I'm going to look at this as d dx of y inside the parentheses cubed, right? Just like we did before. So I'm going to use the chain rule again. Remember, the chain rule has kind of been there all along. It just sometimes, pretty much all the time up to this point, it hasn't showed up until the last section. All right, so here we go. I'm going to do a power rule here, so it's going to be 3 parentheses y squared. But what's unique about this, of course, is, let me fix that parentheses there real quick, sorry. I don't know what the deal with that was. There we go. What's unique about this situation as compared to the other situation, I'm now going to multiply by the d dx of the inside box, the inside function there. So it's going to be d dx of y. So as I finish this out, I'm not going to have quite the same result that I did before. It's going to be 3 parentheses y squared times, well, d dx of y is not 1, it's dy dx. If you look at that notation, you can see that. So here, because I was doing d dx of something that's not an x, in this case it was a y, I'm going to have that chain rule term, or chain rule factor show up. Before, I was doing d dx of x cubed, and because it was d dx of x for the chain rule part, that part doesn't show up because it's just a 1. You can look at this other one here too, d dx of xy squared. Of course, this is a product rule. So here's what I would do with this. I'd say d dx of x times y squared something like that, if we're going to look at this as a chain rule, which we really need to at this point. So it is a product rule overall, so I'm going to just write it as 1d2 plus 2d1. So here's how that would look. 1, of course, is just x. That's my first function. d2, so that means I'm going to be differentiating this factor here. So d2 would be times 2y to the first times dy dx. I differentiated that y term with respect to x, and so I end up with that times dy dx. Well, when I do the other term, it's going to be, so we got 1d2 plus, the other term would be 2d1, so that's going to be y squared. Now d1, that's just going to be ddx of x, which is 1. So in other words, the symbols really matter here. So ddx of x is 1, but ddx of y is dy dx. So we can't just look at it as the derivative. We've got to really think of it as the derivative with respect to x, the derivative with respect to t. We could do the derivative with respect to y. There's all kinds of things we could do with it. Right now we're just doing derivative with respect to x. All right, we're going to go ahead and work on one example here together. In order to do our example, let's check out the steps for implicit differentiation. So step 1, we're looking for dy dx here. Step 1 is to differentiate with respect to x. Step 2, we want to collect all of the dy dx terms on the same side. We're typically going to be factoring out the dy dx and then solving for the dy dx. So we're just going to do one example here kind of as a check for understanding. So let's take a look here at number 1. Okay, so number 1, x squared minus y squared equals 25. It is possible to solve for y on this one. It is not a good idea because you're going to be involving a plus or minus in there when you do that, and it's going to create two really parts of this graph. It's going to be a mess. You're going to struggle to understand, do I use the plus or the minus, and why did I choose it? Do I have to do both? It's far easier to use implicit differentiation. So here's how we do it. We are going to differentiate every term by ddx. All right, so we're going to differentiate with respect to x. So when I differentiate with respect to x, the x squared, let's think about what you get. Should be 2x. ddx of x squared is 2x. But when I differentiate the second term, of course that's not x squared anymore, that's y squared. So the chain rule will actually show up. So it's going to be minus 2y times dy dx. If we wanted to, like I said before, we could have, written what really is happening here. There's truly a dx dx that's right there after the x, but of course dx dx is just 1, and so we would not write that typically, and so we're not going to write that here either. Okay, and then equals the derivative with respect to x of 25, or anything else for that matter. Derivative of a constant is 0. All right, so our final step here is going to be to solve for dy dx. So to do that, I need to subtract the 2x over, so it's going to be negative 2y. dy dx is equal to negative 2x. And then, of course, divide by negative 2y. So dy dx would equal negative 2x over negative 2y, which is just equal x over y. All right, so we will look at a few more implicit differentiation questions when I see you guys next time in class.